The other question I had was, my teacher said that she'd give you a few structures and then she'd ask you to identify which has the higher boiling point.
See, in that case, you have to check the polarity, if there is any polarity within the molecule, and the molar mass. Polarity is responsible for the dipole-dipole attraction.
And molar mass is just London.
Is responsible for London dispersion. If the molecule is too big, then in that case, this London dispersion forces, they become very dominating. And higher the molar mass, higher is the melting point or boiling point. So this London dispersion force, they are for the molar mass, and they are also for the length of the chain. Straight chain, if it is a straight chain, no branching, more London dispersion forces, more attraction.
So the more straight it is, the more London dispersion.
Because more surface area. Because if I give you a chain like this, and if I do the branching, then you can see that how it's becoming smaller. This is smaller. This has more surface area.
Right.
Okay, and if I make it more branched like this, then it becomes more smaller. If I make it more branched like this, then it is more smaller. So the branching makes it more spherical, and you are going from the elongated form to more condensed form, more spherical form. So the branching reduces the surface area and it also reduces the attraction, right? So straight chain, more attraction, higher melting point, and branching will give you less melting. Polarity, you can see if there is heteroatom like oxygen, nitrogen, if these are present. If they are not present, if it's a complete hydrocarbon made up of only hydrogen and carbon, then there is no question of polarity.
So it's only polar in organic chemistry when oxygen or nitrogen is present?
Oxygen, nitrogen, sulfur, these heteroatoms which are more electronegative from someone from here. Fluorine, chlorine, bromine, if they are present, yes. Halogens, then they become polar. And polar compounds,
even if you see them just once?
Yes. What are the examples? Because we have to see the combination of all these factors which I have written here. So what is the question?
Oh, she didn't give us a specific example, but she said she would draw, for example, two structures, and then we just have to identify which one would have a higher boiling point. Okay, like for example, I give you here. Let's say if I give you CH3OH and CH4, who is going to have higher boiling point? The CH3OH, because alcohol generally has a higher boiling point. Yes, if I give you something like this, CH3, CH2, CH2, CH3, CH3, CH, CH2, CH3, and then CH3. Who has higher boiling point? Look at their molar masses. It's same. 4 carbons. So you just have to see which one is polar? No, there is no polarity. Check right, there's no polarity. Check so this one would be it. Yes, okay. But but you said branching is going to have the higher boiling point. Less melting point. See, it's written here. Oh, so this would have higher boiling point. No, branching. This is branching, right? Oh, okay. But what I meant was straight. So the straighter, the more higher boiling point. Because straight has more surface area. More surface area means they are more in touch with each other, better packing with each other. Better packing means difficult to break it. Okay. So simply whichever one has an alcohol, whichever one has more molar mass, whichever one is polar, and whichever one is straighter. That's all you have to look at then? Yes. Okay, well, great. If your teacher, if she gives you something like this, so which one? It would be the one on the right, no? Yes, because it has higher molar mass. Got it. Okay. Just combine all these factors. Okay, so identify the structure. So obviously then, when you're looking for a melting point, it's the opposite. Having no polarity is good. Having less molar mass is good. Being branched is good if you're looking for melting point. Yes.